Hey, welcome. It is Tuesday, April 7th, and welcome to another edition of Kitchen Table Chemistry. And in order to mix it up, I put myself into the upper corner here. Something to do. Okay, we're going to take a look at the combined gas law today and see what that looks like. It is written out as follows. V1, P1, T2 is equal to V2, P2, T1. Initial volume, initial pressure, second temperature is equal to second volume, second pressure, initial temperature. It can also be written as this. V1, P1, T1 is equal to V2, P2 over T2. Like thus, I think most of you will probably use it the way it is written up there at the top. Take a second and jot that down on the back of your periodic table under the heading Combined Gas Law. Also, only moles of gas has to remain constant. So this is going to let everything else change except for moles of gas. And so this is all three gas laws combined together, Boyle's, Charles, and Gay-Lussac's. Now, the combined gas law is really great in situations like this. So here we have a research balloon, and this balloon is going to ascend way up in the air. And when it does, right now it's at it's around 1 atmosphere of pressure because it's at ground level. So it's probably its temperature is whatever the ground temperature is. So say, it's a nice day outside today. It's about low 20 Celsius by this afternoon, 293 Kelvin. Then it's going to go up to some high altitude. And let's say it goes up like maybe 10 miles up. As it goes up 10 miles, the pressure is going to go down to a fraction of what it was, like maybe 0.1 atmosphere or less. So that's going to cause a huge amount of expansion. Plus the temperature, maybe minus 50 degrees Celsius, the temperature is going to go down quite a bit. The change in, for something like this, the change in the pressure is drastic. That's why these things look so underinflated when they take off. And then in a high atmosphere, they actually have to bleed out the helium that's inside of them so that they don't burst. Here is an example. Now, in this example here, what we're going to see, let's see here. Let's put me over here. Okay. And V1 here is going to be 30 liters. P1 is going to be 150 kilopascals. And then T1 is going to be 40 degrees Celsius. And that 40 degrees Celsius is equal to 313 Kelvin. V2 is the thing we're trying to find. So that's our X. P2 here, now it says standard temperature and pressure. So P2 here will be standard pressure in kPa, which is 101.3 kPa. That will be standard pressure in kilopascals, as you would remember from last week. T2 is standard temperature, which is 0 degrees Celsius, and that would be 273 Kelvin. And that is always standard temperature. It's always 0 degrees. All right, we put everything in here. We have our 30.0 liters times our pressure of 150 kPa times T2, which is 273 Kelvin, is equal to V2, which is the X, times P2, which is standard pressure, 101.3 kPa, times the initial temperature, which was T1, which is 313 Kelvin. Oop, oh no, which is 313 Kelvin. So V2 will end up equaling 30.0 liters times 150 kilopascals times 273 Kelvin divided by, on the bottom here, 101.3 kilopascals times 313 Kelvin. Now, it helps on the calculator if you bracket this and then you bracket the bottom. And if we do that, we'll get a V2 value. The V2 that I get for this, as I check my notes, is 38.7 liters, and that would be our answer from this. And if we look, liters does not cancel out. Nice job, buddy. Kilopascals does cancel out. K's cancel out. Liters does not cancel out, and therefore that is our answer. All right, one example for you guys today. I think one is enough. I'll also link a second video that I think might be helpful. I hope this is helpful to you. There's a couple examples that I'd like you to work through. And then Wednesday, tomorrow, I think we're going to look at different look at gas loss. Likely no video tomorrow, mostly just some written assignment. Hopefully this finds you well. You're working on your extra credit or you're not. And again, take care. Hopefully you are doing your very best you. Bye-bye.